Excellent, so quick update on where we're at with the new bench test of some of the components that we're going to use for the RoverBot. I've got some pretty cool hardware here actually, so let's have a look. So what I've ended up buying for now is I've got a RoboClaw, which is it's able to manage 2 motors and it's able to take 30 amps, so it can drive some fairly large motors, brushed motors. I've got a bus servo adapter here. So that bus servo adapter is responsible for talking over UART to, or USB, but in my case UART to many servos, and I have a smart servo here that's just connected to the adapter. You can see here that I've also got it's a brushed motor that's connected to the controller board here, the RoboClaw, and everything is connected back to the ESP32 S3 dev kit, which is a bigger board that gives me lots more GPIO, back to that over UART, which is all configurable. Now what I've got here is an architecture that allows me to, in an event-driven way, do work. So I've used FreeRTOS now, and I have everything written around tasks and queues. And I have a simple UDP protocol. It's literally just text over UDP that I can send to the rover on the rover's Wi-Fi network. So the rover brings up a RoverBot network, and I connect to that, and then I'm able to issue simple commands like I've got a simple Python driver here. So I've got a rover client Python, and then I pass a command like drive 5300, and that's just to test end-to-end connectivity. And so what happens is that is issued on the local laptop to the local IP address of the ESP32, which is listening on, I think, 192.168.1.4 or something like that. Then that goes into a queue, which I call a packet queue. It's obviously there's something on this, the firmware is listening on a UDP socket or a datagram socket. And so once it sees that come through, it then takes the packet, puts it onto a packet queue. The packet queue is then read by a Wi-Fi task. Now currently the Wi-Fi task wakes every 50 milliseconds, so there is a small delay or lag or jitter. It's not jitter, it's more just I guess a delay or a lag there. And then that thing takes the packet off the queue and does some work and sends it to a control queue, and the control queue parses that and does some simple rule-based analysis, and if it can parse it and see and ascertain that there should be a motor control, it puts a motor command on a motor queue, and if it sees something that it can understand as a servo command, it parses that and puts the relevant command onto a servo queue. So you can sort of see how I've got everything decoupled around queues, and I have each task, like the Wi-Fi task, just owns the Wi-Fi channel and UDP communication. It doesn't understand anything about the packet, it just puts it onto a packet queue. The control task is responsible for reading anything that's on the packet queue, and it understands and parses the command, so it understands what drive 5300 means. And right now it doesn't mean a lot. This is really not the final protocol. This is just for me to test this architecture, and so it's then able to parse and put that on the respective queue. Then I have a motor and a servo task each. They are responsible for talking to the hardware. So the motor task knows how to talk to the RoboClaw via the drivers that I was able to get, and so the drivers for that are supplied open source as part of Basic Micro's open source driver package for them, and then I have another driver package for the servo adapter board here, which SC Servo I think it was called, and so that lets me talk UART and a bunch of different protocols, but in my case just UART. So the servo and motor tasks themselves are they instantiate a servo and a motor driver, and that driver is the interface that I talk to, where I have all the other hardware-specific driver details behind, and then the task itself does the work. So what I could do is I can send a drive command. Okay, that you can see that it said contacting Rover at that address on that port, and it sent 14 bytes. You can see a whole bunch of output here as a result of the command. If I just clear it and we can have a look, probably just a better look at what is going on here. So let's do it again. All right, so the motor driver said it set the duty for motor 1 to 0, and it succeeded. That's a stop. Then a message was received, drive 5300, that's great. That was sent to the packet queue. The Wi-Fi task did that. The control task then worked out that there was a drive command type, and then it on-queued to the motor and servo queues these values, and then that was the command task, and then the control task queued the motor action and the servo action. These are sort of out of order, but that's okay. And then the motor task ran a motor action, and then you can see the driver actually doing something where it's setting the duty to 5000. So, and the servo did the same thing. So it turns the servo from a particular position, which is about middle, to turn it 300. So let's have a look at it in action. So if we run it again, let's run the CLI, and then we have a look over here at the hardware. You can see things are just moving. It's pretty nice and simple. So you can see the motor moves, the servo moves, with a small delay. I need to do a lot more work on the timing, but you can see that they are kicking off at the same time. The servo moves and then it moves back. The motor just moves and stops. All right, so if I hit enter again, I haven't set acceleration. This is an open loop, if you like. There's no feedback. Both this servo and the motor. The motor has an encoder on it, magnetic encoder. The servo can give me readings as well. So over UART, I can understand precisely what is happening to the actuators, and I can do closed loop control. In fact, the RoboClaw board does PID for me. It does a whole bunch of stuff. This is almost like learning a microcontroller in itself. It looks really powerful, and it's pretty exciting to kind of learn this stuff. The servo adapter, the bus servo adapter board, has less control, but it still does a lot of the smarts for me. So it won't go past the end of the servo range, if you like. It'll stop, and if I send commands and the position is already at the maximum position, it won't move. So it doesn't overflow or doesn't do anything bad to the actuator. So that's where we're at the moment, and I'm just running everything off the power supply at the moment, which is 2 channels, 12 volts at current limited to 0.5 amp. And that's all messy, but into these 2 boards, and I'm talking UDP. So this is broadcasting a Wi-Fi AP. I connect to that, I send UDP packets to that. It, in an event-driven way and in a nicely decoupled way, parses that and sends the right commands around the system for the actuators to do the right thing. What I like about this design at the moment is that each subsystem is owned by a task, and there's no sharing of state across those tasks currently. I have decoupled all of those. All the state that is effectively moved between tasks is all done via queues right now. I mean, I can have shared structs and things that I need to, be careful around thread safety and use mutexes and what have you around those. But right now, I don't need to do any of that because I'm just decoupling everything via queues. So that's been really nice, and that's where we're at the moment. And the plan is to continue with this architecture, and then eventually next week bring up a single corner where I probably mount this. Currently it's just obviously a mess of wires on the board, and I'm testing the firmware. I started writing the firmware about 5 days ago, and then I received the parts, and I've been just doing the basic reading to wire this up appropriately. But within sort of 5 days, I've got a pretty scalable, fairly clean decoupled task queue-based FreeRTOS architecture, which is much, much nicer than the standard Arduino loop, and sort of sharing global state, and it gets messy very quickly. So that is I believe that's a nice scalable architecture. and then the hardware itself is, I think, appropriate. And what I'll end up having is another RoboClaw. They're not cheap, they're like $250 each or something, but I'll have another one of those. Each of these can control 2 motors, so that'll give me independent control over the four motors on the rover. They can all connect back to the same UART, or let me restate, I can control multiple RoboClaws off the same UART. I think up to 8, and I only need 2, so I can have everything connected via the same hardware UART on the ESP32S3 dev kit board for the motor control. And then I'll need 3 more of these, of course. This gives me the ability to, I think, daisy chain 256 servos or something crazy or more. I think I'm only going to use 2 servos. Originally I was going to go 4-wheel drive and 4-wheel steer. I think what I'll do is do 4-wheel drive, and then I'll have 2 servos so that I can have 4-wheel steer but not independent steer. And I'll have a coupling where I have the two front wheels steering together with a single servo and the 2 back wheels steering together. And I think that's probably the simpler architecture for now, rather than worrying about 4 servos. But I could do that later, and I could do that with this hardware. So that's nice. And then once I've tested, I'll probably bench test this a bit better over the next week. Write some kind of safety code in here. There's nothing in here that kind of keeps things within range, or there's no such thing as a safety stop or an and-on cord or anything like that. So I'll probably build that in, and then start to design the power distribution board. So what I'm going to do with this one, because I'm offloading to these parts, I'll probably I'll have one of these at the front and one of these at the back on the chassis. I'll have this in the middle somewhere, and then I'll have the ESP32 on a carrier board that has an IMU. I'll need an IMU, of course, and I'll have some passive buzzers and LEDs and things like that for control and just notification. And then so basically what I'll have is I'll have a logic board with the ESP and IMU and stuff on it. I'll have a power distribution board or a power board, which just takes power in, because I'll end up having 2 bucks on there, at least. 1 buck that goes down to 5 volts for logic, or for ESP rather, to power that with 5 volts in. And then I'll need a 24 or maybe a 12 volt rail. I'll have to think about that. So what I'll end up doing is I'll standardize on 6S, which I don't know what that is. Let's call it 26 volts. I don't know, 24 volts, 26 volts, something like that. So what I'll have is I'll have a 24 volt rail. I'll have a 12 volt rail, a 5 volt rail, and then a 3.3. So there's a bit of power distribution to get right there. And I'll have that on a single board. And I'll do things there like ensure that I can still plug into the ESP over USB for serial. I don't know, I need to think about how I'm going to do that, but I want the power distribution to be a separate board and safe. And so I'll do that as a separate schematic. I'm going to start to do those in KiCad just as schematics, and I'll start with the power board, and then I'll do the logic board, which is just really a carrier board for these parts. And then the rest will just be wiring out to these other components and the actuators. So it should be a kind of a fairly simple but modular board design as well, and lay that out. Then I have to do the mechanical piece for how each wheel or each corner will turn, and I've already got some ideas for what I'm going to do there. I'm going to avoid direct drive, but I have to think about what I want to do there. So anyway, that's where we're at. I thought I'd give you a quick update, and it's been a lot of fun. 5 days in, let's say, and making some good progress.